Welcome to the new faculty lecture for today. It's our great pleasure to have with us our new colleague, relatively new colleague, Volker Blum, who did his PhD at Erlangen and Nuremberg, then did his postdoc at NREL, the National Renewable Energy Lab in Golden, Colorado, and then returned to Berlin, where he was a member of the Max Planck Institute and became the group leader for computational materials, particularly with respect to quantum mechanical models. And among other things, he's been tutoring some of us this semester who always wanted to know more about quantum mechanics than we knew before. And he's been very patient and very helpful. And I'm very much looking forward to his talk today, as I'm sure you are as well. So please welcome Volker Blum.
Thank you very much. Thank you very much for the introduction, in fact, and thank you very much for coming to my lecture. So you've heard that my name is Volker Blum, and that I joined the MEMS department in September. Before that, I was a group leader at the Fritz Haber Institute of the Max Planck Society for 9 years, which is an institute that's situated somewhere between condensed matter physics, physical chemistry, and material science. And that last aspect is, I believe, what brought me here. So the title of my lecture is An Integrated First Principles Vision for Materials, Nanostructures, and the Properties that they control. And I'll spend the next 45 minutes or so talking about that vision and why it is useful. Now, by first principles, I mean quantum mechanics, which is a mathematical framework that gives us a recipe, a mathematical recipe that's in principle exact to predict the properties of any materials around us if we have a large enough computer. Now, if you know anything about quantum mechanics, this theory starts from the atoms and electrons, so it's not a wise idea to tackle a macroscopic object outright, such as a bridge, a computer chip, or maybe an industrial catalyst. But if we use it wisely, we can learn a lot about the materials that would make up a bridge, a computer chip, or a catalyst. For instance, something about the reactive sites in a catalyst and the limits or acceleration of a reaction that it tries to do. So this is a whole new way of looking at materials and their properties from the ground up, and also how to make them better. And this is what this vision is about. Let me give you a brief outline of what I'm going to do during this talk. I'll first say a few words about the basics, first principles computational material science and what that field is. And what you see here is the kind of founding equation of quantum mechanics in its shortest form. That is Schrödinger's equation. And you also see Schrödinger, who's over here. But I put another person on, and this is this guy here, whose name is Walter Kohn. And in the 1960s, he formalized a concept called density functional theory that I'll say a little bit more about later. And this density functional theory in material science is, I believe, what made first principles as successful as it is today in that field. He also received the Nobel Prize in 1999 in chemistry for his contributions. Then I'll say a few more words about how we can use this to learn something about real materials on real computers. One thing that one needs to know about this field is that the quantum mechanics here is usually embodied in the form of large, powerful computer codes, and I happen to be the lead author of one of them called FHI AIMS. FHI stands for the institute that this originated at, the Fritz Haber Institute, and AIMS stands for Ab initio molecular simulations. And how many people had Latin here? Anybody? One? Excellent. So for the people that didn't study Latin, ab initio is another way of saying first principles. And finally, I'll come to a specific example of research that we do with this on two-dimensional materials. Now, the poster child for two-dimensional materials is graphene, and happens to grow particularly well on a semiconductor material called silicon carbide. And I'll say some words about that in the end, why that is, and how we can potentially even improve this growth. But before I do all that, let me take a step back and come to a little bit more broad statement, which is that if we had a theory that could predict the right materials or molecules for a given task, then we could dramatically accelerate the rate at which better materials are found. And I didn't make that statement up. This is a lot of what people pursue today. And this is actually, I think, a sentence that's codified inside this materials genome initiative that was endorsed by the White House about 2 years back. And I've just taken the liberty of copying the front page of their vision statement, which gives you an idea of how broad that vision is really supposed to be. It ranges from heavy industrial materials such as steel via microelectronics, all the way to energy and environmentally relevant materials, for instance, solar cell materials. Now, if we had such a theory, and happily, it turns out, I just said that we have just such a theory in the form of quantum mechanics. So here is, again, the basic equation, Schrödinger's, or actually Dirac's equation, which is a little bit more accurate in its short form. Dirac, in fact, is an interesting character in the beginning of quantum mechanics because not only did he come up with the form of the equation that basically covers all sorts of materials these days, but he also, as early as 1929, made this visionary statement here, which I'm going to read out from a paper of his. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And then he goes on to say that it's unfortunately a little bit computationally complex, so it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. And this is really a visionary statement in the sense that this is exactly what the field has been doing for the past 80, 85 years or so. Now, what does this mean for our theorists today? I call this a theoretician's dream of finding better compounds, because one thing we would really like to do is to specify simply a target property Y of some material and then predict without much input the best material or molecule X to find this target property. And there is a good way of accomplishing this task, which is if we had a library of all chemical compounds, the known ones and the unknown ones, we could simply pick a book from this library and find the material that is the right one for our purposes. This is, of course, not a new idea. This has been long done in experimental science by tabulating materials and their properties. And also in empirical theory, interpolation, or simply intuition that's been so successful in materials developments over the, well, I guess the history of mankind in a sense. But there's also this little corner here that is becoming more popular, which is first principles derived structures and properties that we can also add to the library. We can do this in two ways. We could first just try a brute force screening of all materials, and some people do this very successfully, including here at Duke, except that you realize that if you try all materials, this runs out of steam relatively quickly for complex materials if the number of atoms becomes large, because the structure space grows exponentially. So there's also the second way, studying individual systems in depth, that can be used to populate this library. But one thing that both approaches need is the underlying input. And this is where my work largely happens, trying to provide this first principles computational input. And what is important about this input is that if we want it to be useful, we must be sure that we actually compute what experiment would find. And this is a difficult statement, and this is an ongoing challenge to the field, of course, but that's what we have to do. So let me first say that this is a rather successful approach in many respects today. You can do a lot of things. For instance, you could want to try to answer the simple question here, given a compound's composition, AX, B1 minus X, what is its low temperature stable structure? And the simplest answer to give is to try to synthesize that material and go to an experimentalist who happens to do X-ray diffraction and get him to hopefully find out something about the structure. But in subsets of structure space, there are actually rather successful first principle strategies these days too to do this. For instance, binary alloys on a lattice. So if you just take a lattice and color the sites with red or yellow balls, which are the different elements, or equivalently give them pluses or minus ones for the element that occupy this lattice, then you also get compounds, and these are not completely irrelevant. In fact, this is what makes up substitutional alloys, intermetallic compounds, and so forth. So this is a rather large part of materials, in fact. And all you need to solve this puzzle is the internal energy of each of these configurations, because you just find the lowest energy configuration, and that's the most stable structure at a given composition. Now, with first principles methods today, we can calculate hundreds of formation enthalpies for such structures. We might be able to calculate thousands or 10,000s, but you realize that on a real lattice, if this has n sites, the number of decorations of this lattice is 2 to the power of n. So this grows exponentially, and this is something that's a hard problem, even with the fast computers that we have today. Fortunately, there is, in this case, a way to get around the problem and solve it in a more effective way, which is called a cluster expansion, where you basically take these energies here, these configurational energies, and map them onto a different expression. So this expression over here contains sums over individual lattice sites, and it contains the sigmas that you see here and interaction parameters called J. And if you use this as a mathematical formula, you find things like pairwise interactions between the atoms, 3-body, 4-body, 5-body. And the nice thing that this is in principle an exact rewrite of the energy if you knew all the interactions. The other nice thing is that, of course, you hope that you won't need all these interactions, for instance, over the length of 2 feet or so. So at some point, this is going to be short range, and you can use this to create reduced models. You could, as a recipe, for instance, simply calculate the total energies of, say, a few hundreds of these structures here, then throw them into the Hamiltonian, so into the expression that I just showed you. This is a reduced form of that, but the J's are here again, and fit the effective model parameters J. This connects back to the last new faculty lecture, actually, because compressive sensing, which Galen Reeves talked about, is the latest thing to do this effectively and obtain reduced models of this kind. Once you do this, you find stable structures for relatively simple alloy systems like tantalum tungsten, for instance, that look interesting, but they look nowhere as simple as those that we put in. And these are also not structures I, at least, would have first guessed as the stable structures, yet they come out. Now, this is work done about 10 years ago. In the meantime, we have a lot more computer power and a lot more knowledge. And we can do this not just for one alloy system, tantalum tungsten, but, for instance, for 1,300 of them. Gus Hart, Lance Nelson, and Stefano Corterolo here of Duke did that and are in the process of doing that, I believe, with hundreds of input structures each. And once this is done, this part of the materials genome is, in fact, close to solved. Now, that leads me to a simple recipe for materials development. This is, don't judge me just yet. We specify the desired material properties in the rough range of materials. We find a big computer to put in h psi equals e psi, and out falls the finished material with optimum target properties. This would be nice, and we all know that it's not so simple. First of all, there's the issue of structure size. So even conceptually simple materials like graphene on silicon carbide can have complex structures, so structure space is large. But second, the argument that I just made about minimum energies relies on energy differences, and these can be subtle between different structures. And current methods can fail even qualitatively, with or without warning, for certain of these structures. And that's an ongoing challenge for the community. So we certainly need this third aspect here, which is constant validation of the theories by connecting to experiment as much as we can do. And this is what is usually done in the field. Now, what do these more complex materials look like? I here have 2 examples. One of them is the side of, in quotes, biomolecular materials. What I'm showing you here is so-called secondary structure elements that make up proteins. So they're just the building blocks, but even these helices, which is this cartoon ribbon here, ferns or sheets, have hundreds of atoms by themselves. So the systems are large, the conformational energy is very subtle, and they happen at finite temperature and in an environment of a solvent. So this is not trivial at all. And similarly, for nanostructured systems, such as this nanostructured graphene and silicon carbide interface, at least the material is solid, but still, we'd like to take a large system and predict electronic, mechanical, catalytic, and so on properties, look at stability of certain structures, for instance, the growth process by which the structure emerges, and how we can manipulate this to do something new. And what we have to do that, in this case, is, again, Schrödinger's equation. And in particular, this object E here, which is the total internal energy of the system in a given state. But if we can calculate this, we can do statistical averages. We can do things like free energies or Gibbs free energies in certain approximations, electronic excitations, and so on. So the science that we used to, we just have to do the computations. How do we do this at this point in practice? This is what I would naively call the current state of workhorse electronic structure theory. There's first the traditional approach that is here labeled quantum chemistry or many-body theory, which is to take Schrödinger's equation and solve it for this object here, which is psi, the so-called wave function. This is a complex object, but you can successively refine it, except it gets very expensive if you want to do this exactly. If you really want to solve it exactly, you can do this for 7, maybe 10 electrons, I think, at this point, and one can argue whether it's a little bit more or less. There are more approximate methods along these lines that get you a little bit larger, but we need approximations. And one of these approximations that was successful in material science, I mentioned before, is density functional theory. This was codified in the form of the Hohenberg-Kohn theorem in 1964, or Kohn-Sham. So there's Walter Kohn again, the Kohn-Sham equations in 1965. And here the idea was simple. What Kohn and Hohenberg proved essentially is that you don't necessarily need to know this wave function in principle. What you need to know is the density. This is a three-dimensional object, so this is something we can fathom. The electron density or particle density of a system, this is an observable, and then this energy here is uniquely connected to this. So this here is written by way of a so-called functional, which means that you don't exactly know, in this case, how to make this connection rigorously. It's not a simple function, but if you know the density, in principle, there exists such a functional, and happily there exist approximations that you can use to make this practical. One of them is this expression here, which is taken from Kohn-Sham theory. And the key point here is that these three parts are things that we can simply calculate. It's a single particle kinetic energy in detail. It's a potential term, which is a simple integral. And it's the electrostatic interaction of electrons and nuclei on average, which is also solvable by Poisson's equation. But then there's an unknown part. And to solve that exactly, we'd really have to go back here to this full equation. But we can approximate it. And I call this EXC of n. And the key point is that EXC is small. It's not small compared to chemical energies, but it's small enough for us to work with, or else the field wouldn't have taken off. So let me just quickly give you a list of the approximation hierarchies that we use in the field today. I call this here Purdue's ladder to the exact solution, because John Purdue, I think, showed this picture first. And each rung of this ladder corresponds to an approximation with a given accuracy, but also a given cost, and the cost and accuracy hopefully increase. The cost certainly does as you go up the rungs of the ladder. And the basic rung of this ladder in the density functional theory is typically called the local density approximation. And this really this functional depends only on the knowledge of this density explicitly, and that's what you do. Now you can refine this a little bit by making the functional depend also on the gradients, maybe second order gradients, and so on. And you can also bring in some pieces that are known in quantum chemistry, such as so-called non-local exact exchange, which is part of Hartree-Fock theory for those who've heard of that, and kind of mix quantum chemistry and density functional theory in its original sense to form so-called hybrid functionals. That's called generalized Kohn-Sham. And if you want to go further, you can go the route of so-called many-body theory. So these were things that were developed in condensed matter physics in the 1950s, the random phase approximation, RPA, or second-order screen exchange. And if you go that route the whole way, one hopefully will arrive through the back door again at this equation here, but also at the cost. So these are relatively expensive high-level methods, whereas these are the workhorse methods that we would like to use in practice. But we can use these and do use these for validation of what we find, so they're very important in case the theory fails. So you see, there's already a relative zoo, and that zoo actually becomes a little bit larger in this kind of summary of where my personal summary of where density functional theory is today, I think. It really is a reliable baseline method for many phenomena, but there is this zoo of different methods. And in fact, so this word cloud here are different approximations, or abbreviations of different approximations for density functionals that are out there in the literature, this EXC of n. There's a DFT popularity poll out there that collects these and annually elects a winner. In 2012, the non-empirical PBE functional is the surprising winner of this year. So that's what you can find. But that said, while there is this zoo, if you use this theory wisely, this is an immensely successful approach to get quantum mechanics-based, non-empirical, material-specific predictions for the right reasons if you know what the underlying theory is. And that's what we try to do. Now, the second part of the talk is how do we do this? How do we do this on a real computer? And this is kind of my personal angle because, of course, that is what I do. And I said already that we began a new electronic structure code in 2004, 9 years ago, which has become a relatively large thing, as you'll see in a moment. But if you want to do this from scratch, you better have a good set of goals that you want to work with, or else this is maybe a bit too large of a project. So we had a set of goals, and one thing was universality, in the sense that we wanted to start with a recipe that would give us access to the entirety of materials chemistry at the outset, at least from a numerical point of view. So trying to get something on equal footing that are light elements in organic and molecular science, 3D transition metals with magnetism, 4D and 5D transition metals where catalytic properties are important, perhaps F-electron systems, lanthanides and actinides, which in many respects are problems for the theory itself, for density functional theory itself even today. But at least we wanted a numerical framework that would capture all these. And hopefully in all sorts of geometries. I call this here materials and molecules, but really what I mean is periodically repeated or non-periodic structural models. And this is often a place where different codes in the community separate themselves one way or the other, but not both. So we try to do both. We wanted the whole hierarchy of methods that I just showed you, simple density functionals to high-level benchmark methods. And we wanted an all-electron method for the system. And something that is scalable, not just with respect to system size, where we're perhaps at thousands of atoms at this point, but also with respect to computer size. So if we have we can run this on a laptop, but if we have a computer with 2,000 or 20,000 CPU cores, we should be able to use it efficiently. And finally, perhaps the most important statement that I at least had in mind while developing all this, that we wanted something that's efficient, but not efficient at the price of terminally sacrificing accuracy. So the basic idea is that if you make an approximation, at least in a numerical sense, you should be able to undo this approximation for the real system in question if you really want to. And that in detail is a hard goal to follow, but that's what we try. Well, what is the basics of that? I'll just give you a brief flavor, and this is the only equation that I'll show in this talk. This is actually what the Kohn-Sham equations look like in practice if you want to solve them. They're really just partial differential equations. It looks actually like Schrödinger's equation for a single particle. It has 3 dimensions, so this r here is a 3-dimensional coordinate. And it's an eigenvalue problem, which means that you'd like to solve it for these eigenvalues epsilon k here, and these eigenfunctions psi k here. The trick is that it's a nonlinear eigenvalue problem in the sense that the terms over here depend on the solutions. But for practical purposes, what you need to do is to discretize a 3-dimensional partial differential equations. In quantum mechanics, we typically call this discretization a basis set expansion. So you find a finite set of functions phi I in which to expand your possible solutions. And once these functions are chosen and they're finite, the whole problem becomes a matrix problem, an eigenvalue matrix problem. I'm writing this here using integrals in quantum mechanical notation, but they're really just 3-dimensional integrals to solve. And this eigenvalue equation here has a matrix when things are double underlined and a vector when things are singly underlined. So this is a matrix, this is an eigenvector, here's the eigenvalue, here's an overlap matrix which is often diagonal, here's another eigenvector. This is traditional linear algebra that you learn that you can solve with standard computational libraries once you have it. The question is how to discretize. There are many good options out there. Plane waves in the materials community are perhaps the most used ones in codes like VASP or ABINIT. The quantum chemical community has been successful because of the use of Gaussian orbitals, which have nice analytical properties. But there are many more ways of doing this that are used today. There's something called augmented plane waves, which gets all of the electrons back into the game compared to plane waves, which just use a subset. Wavelets are finite elements, traditional things that you encounter in partial differential equations. And something called numeric atom-centered basis functions that we chose to use. I won't say much about what these are, except that this is the functional form, and that their basic advantage is that they give you relatively small basis sets to solve the problem for chemical systems with high accuracy, and that's the property that we make use of, and that's what all this is built on. So let me fast forward you briefly through where all this is in 2013. This code effort has morphed into a large, successful, I hope, collaborative effort. We have a code that does all electron density functional theory and beyond for the materials we want to do. It's based on these numeric atom-centered basis sets, which essentially gives you one framework to go from fast qualitative high throughput calculations, if you want to, all the way up to highest accuracy numerically, at least converged results if you need them. It goes seamlessly from light to heavy elements. and it treats molecules, periodic systems, surfaces, nanostructures, and so on equal footing as we wanted. It has the approximations of density functional theory that we're interested in, some things about van der Waals interactions, which are very important in many systems, including graphene, in fact, and then many-body perturbation-based validation methods, some of which I mentioned before, some from quantum chemistry, like Möller-Plesset theory here, the random phase approximation. GW is a technique to get you electronically excited states. Linear response, time-dependent density functional theory gets you at optical excitations to some extent. And we're working on all these as we go along. The code was built to be scalable, and for density functional theory, it scales up to several thousands of atoms at this point. But also, the computational scalability on the computers that we have was an important point. So it can routinely be used on hundreds to thousands of CPU cores, which is good to speed up practical calculations. But it's been demonstrated up to 262,000 CPU cores. And a lot of that was due to an eigenvalue solver library that we developed along the way called ALPA that solved a few of the scalability bottlenecks for us, and that is now an open source library. We have things that we need, like structure optimization, finding the minimum energy structure in a local sense, or molecular dynamics to get statistical averages, and then a whole slew of properties and functions that I don't list completely here. But things like vibrations and phonons are typical to calculate free energies in various approximations, infrared spectra, work functions, which is the energy to get an electron out of a surface. Electronic and thermal transport are connected in some sense to the code, and many, many more that are there. Now, I talked about scalability. Let me just show you what this means in practice for a model system, which is, in this case, I call it a model biomolecule because it really is made up of an amino acid repeated 200 times, alanine. So this gives you 2003 atoms. Most importantly, these numbers here mean the size of the basis set or matrix problem in the linear algebra. So this is 50,000 for the matrix dimension and about 7,000 for the number of states that we're solving for. And if you run this on a Cray machine, which was done by Ville Havu earlier this year on a new Cray in Helsinki, you see that as a function of CPU cores, the time for these operations in the total time, this is the black line, scales pretty much out to 4,096 CPU cores. If you partition this down into the individual parts, the eigenvalue solution, the green line, really is the dominant part in this case, so the linear algebra pays off. And the other operations here are real space grid-based operations that don't matter so much for the very large systems here. Now, we can use this in many respects. I'll walk you through a few quick examples of what we've actually done in Berlin. Others do many more things. Biomolecular spectroscopy is one thing that we looked at because we were interested in the structure of such molecules and how close we can get. This is what I've drawn here, a helical model of another polyalanine amino acid chain. Oops, excuse me. Here we go again. With a positive charge up here. So this is the helical model again. If we want to see whether this is locally stable, we can just run a molecular dynamics simulation, and it wiggles and wiggles, but it doesn't really fall apart over the space of 26 picoseconds or so. Now, that's not a long time, but we can also turn to our friends, the experimentalists next door, who happen to have access to infrared spectra, which are structure sensitive for molecules in the gas phase. So this is a very good environment for us to compare the results to, because we're doing exactly the same thing. They have a free electron laser, and what you see here in short is in gray the experimental spectrum that can, and in red the theoretical spectrum that can be derived from this expression here from the molecular dynamics trajectory that I just showed you. And in a nutshell, this molecule is indeed helical. At least that's what the spectrum seems to indicate. We can go to the other end of the periodic table and look at something like cerium. Now, cerium is interesting to get right if you're interested in catalysis, but it also has some fundamentally interesting aspects like this phase diagram here, temperature pressure, of just bulk cerium. And you see a bunch of phases, and in particular this alpha gamma here, which are structurally identical, except that if you go down in temperature, at some point the volume simply collapses into a different phase. And this volume collapse is one of the cases where traditional density functional theory, for instance in the local density approximation, simply fails. They get one phase but not the other. But it turns out, as shown in this paper here, that if you use a many-body perturbation method a little bit higher on this fifth rung of the ladder that I showed before, you actually get this transition. We can go to the other end again and look at electronic levels in organic semiconductors. This is, of course, something that people are interested in ultimately for something like photovoltaics. This here is for a trans-polyacetylene model molecule, and this is an experimental photoemission spectrum, just to convince you that we can, if you want to, also use either many-body perturbation theory to calculate the spectrum, or a cheaper, what I call your optimized density functional method to actually get you roughly the same electronic spectra, so we can do something here too. There are many more examples. But at this point, let me step back and come to what will be the final chapter of the talk, which is an example from my own group, which is an example of what we can do, how we can understand a specific important material's property, and hopefully also understand how to make it better. This growth of graphene on silicon carbide that I mentioned before. This work was done by Lydia Nemetz, who's a PhD student in my group, with also involvement of Patrick Rinke, who's another group leader at the Fritz Haber Institute. Now, let me just motivate this problem quickly. The question is simple: how to best grow graphene films on silicon carbide, and why? So it turns out that this growth process does not happen by depositing carbon on top of the material, but actually by heating the substrate until the surface silicon atoms evaporate and leave the carbon behind. And this grows you this graphitic structure up here that you see there, and this is often done in ultra-high vacuum, where the silicon, of course, leaves best. But if you look at this atomic force microscopy image here from the group of Walt de Heer and co-workers at Georgia Tech, you see that the film quality is actually pretty bad. This gets you graphene, monolayer graphene films. You can show that, but not very good. And it turns out that you can do much better if you use other growth techniques. For instance, you can enclose this silicon carbide sample in small cavities so that you have a finite pressure silicon vapor around it, and try this again. And then it so happens that these films grow much better. On a naive level, this would seem counterintuitive because you're offering silicon and you're growing a carbon structure better. So why is that? And of course, we can find an answer to that. Let me just walk you through the growth process a little bit more slowly next. There are many ways to grow graphene, but this is actually one of the oldest that I showed you here, the high temperature sublimation of silicon. Basically, you prepare your silicon carbide surface, and then you evaporate away the first three planes by heating of silicon here. You leave behind the carbon atoms, and what you get is a structure that looks like this. This up here is carbon atoms. It's not yet graphene, in fact, because it's covalently bonded to the substrate. But if you heat a little bit more, this layer lifts off. The next layer of silicon atoms evaporates somehow, and you get the same interface, but underneath a graphene plane, and so on, or bilayer, and so on. Now, this is a practical thing because it really creates graphene directly on a semiconducting substrate, so you can use the normal tools of semiconductor science to do something with it. This is an example of a field effect transistor that was made by just using graphene as the kind of metal contact to the transistor and making the transistor out of silicon carbide. Just briefly, what is labeled contact graphene here is the monolayer graphene that I just showed you. This gate graphene here is the same thing, but additionally there's a layer of hydrogen atoms intercalated that electronically insulates it from the substrate. But that, in a nutshell, in this paper produces a current voltage characteristics that looks like a field effect transistor. So this is useful. Again, we want to grow it. And I already told you that if you just grow this in ultra-high vacuum, you end up with pretty inferior quality films. That's well established in the entire community. And in fact, in 2009, a partial solution to this problem came along from a group in Erlangen around Thomas Seiler and co-workers that showed that you could significantly improve the growth morphology if you grew at a higher temperature in an argon atmosphere, so not in vacuum. And then there's the De Heer group, who have used their cavity growth recipe that they published in 2011 for a long time in a silicon background. Also, temperature and pressure play a role. And when temperature and pressure come into the game, it somehow sounds like thermodynamics. And in fact, there's a publication from an IBM group from 2009 that draws a temperature-pressure phase diagram for silicon carbide surfaces. What you see here is different surface structures that are stable at different temperature-pressure conditions. 3 by 3, 1 by 1, square root 3 by square root 3 are just labels of structures that are not yet graphitic. But importantly, this zero-layer graphene that I showed you before also has a stable temperature-pressure range. Now, the question is, of course, can we also draw monolayer and perhaps bilayer graphene into this phase diagram? Experimentally, you can't because it's pretty difficult to revert the growth of a graphene plane just by waiting, so reversibility is hard to show. But in theory, we can test this hypothesis by doing calculations. And the essential calculation that we need to start is quite simple. We need to calculate the surface energy of different surfaces and find out which one has the lowest energy. We can calculate the total energy of a so-called slab model of the surface structure. And then we can calculate the surface energy by subtracting the energies of the individual atoms that make up this model, whether they come from the silicon carbide bulk or from elsewhere. So these are formal parameters here that stand for the energy of these atoms, which are known as chemical potentials in thermodynamics, the reservoir energies, if you will, of these atoms. There's one condition that couples those chemical potentials, which is that the bulk has to be stable, so their sum has to be equal to a silicon carbide unit cell. But the difference isn't clear, so you get an experimentally controllable parameter, and this is, of course, the gist of thermodynamics or physical chemistry, that you can play with these things by adjusting things like temperature and pressure. This is exactly what we want to do. Now, there are some stability boundaries that we can state, which is that if the carbon chemical potential was less than the energy of a carbon bulk, you could basically generate energy by destroying your system, and similarly for silicon. So you don't want to do this. This gives you boundaries, and within that, you can calculate the surface energies of these phases to investigate stability. We can do standard, in quotes, calculations in density functional theory here by so-called slab models made up of 6 bilayers and the surface phases. We can use high accuracy numerical settings and a density functional that includes van der Waals effects, which is important for the graphene in this case. But the key point is that these structures are large. So if you look at the actual unit cell that you can use for such a model, from top, you see this thing here, which is a 13 by 13 graphene plane based on a 6 square root 3 by 6 square root 3 silicon carbide model. And this is just a lot of atoms that you have to handle, even in the smallest case, 1,700 up to 2,700 atoms for the largest thing that we calculated. And that for subtle energy differences, but we can do this. And I'm drawing the results here in a so-called surface phase diagram as a function of the carbon chemical potential on the x-axis. What you see here is the surface energies, and at a given chemical potential, the stable phase is the one with the lowest energy. You see that there are these 3 by 3 and square root 3 by square root 3 phases, which I mentioned before. They're not yet graphene. This one is the lowest energy stable phase in this range. This one is here. And then we come to the carbon-rich limit around graphite. And if we draw in our zero-layer graphene structure, we find that in a very narrow range over here, it actually crosses and becomes the lowest energy structure. If we go closer to the graphite limit, monolayer graphene also becomes stable, and bilayer, trilayer we can also draw into this. So if we zoom this out, we get a very narrow range where either zero-layer graphene or monolayer graphene is stable. Now this is in agreement with the experiment, that there is a phase area where you can grow this as this thermodynamically stable phase. For monolayer graphene, we also find such a phase. I have to say that these energy differences here are very subtle. So this is certainly inside the error limits of what we can do from density functional theory today. But what this means is that there is either a stable phase or something that is very near thermodynamic stability. So in more practical terms, going back to the picture from the beginning, if the chemical potentials are meaningless parameters for someone, what it really means is that we can understand this by just looking at the formalism. If there's a chemical potential at which monolayer graphene is the most stable phase, then that will correspond to some experimentally accessible temperature pressure conditions, and we have to find these to know where monolayer graphene will essentially grow on its own if the temperature is high enough. And that's what is used in experiment and could be used to refine this. More importantly, it's also useful to know that a certain phase is not the stable phase, because then you have to do something else to grow it. This happens on the other side of the crystal, for example. So this is something one can use to perhaps speed up what phases are found by what way and not another way in practice. Here, certainly, it would have made a difference to know this 10 years earlier, because that was the way to go. Now, this brings me almost to the summary of the talk. This is the library again, and what I'm trying to say in a broader vision, what we're trying to add to this library is efficient, accurate first principles understanding for real materials and processes. And in the big picture scheme, this hopefully will accelerate the development of what I call here better materials for many challenges that we face. Electronics is one thing that I talked about in the silicon carbide sense, but I also mentioned energy challenges and the environment. These are all the areas that people are active in today. My one ongoing push is to try and increase the reach of our methods, density functional theory and beyond, for the large nanostructures that we would like to simulate. Graphene on silicon carbide is one example that I talked about. 2D materials in general are very popular these days and offer a lot more opportunity for research if we can reliably model them. So let me give you one example where this might be of interest, and this is the creation of hydrogen, so fuel from solar energy. This is an old dream, and you take a bottle with an acid, shine sunlight on it, and out comes hydrogen that you can then use to produce fuel. It's not a completely crazy dream because it works in the UV range, in the ultraviolet range with titanium dioxide. But what you'd really like to have is a catalyst that facilitates this, another catalyst that facilitates this with visible light. This is a problem that a lot of people are working on, and I'm just showing you here a complicated picture from a Chinese group. Excuse the complications up here. They're actually very necessary. But if you just focus on this thing down here, this is in fact a graphene sheet, and the catalyst particle that they use, the nanocatalyst in this case, is molybdenum disulfide. And this is in fact photoactive in the visible. So this is something one can do, and more importantly, one might perhaps be able to use theory to predict better photocatalysts for this thing and point out what would be useful. That's a realistic prospect. So with that, I come back to my summary slide. I thank you for your attention. Funding agencies were also involved at various stages, and otherwise, I would be happy to hear questions.
We're open for questions. Are there questions?
Question. In the ladder diagram that you showed, you talked about cost, you also talked about accuracy. So when you say cost, are those primarily the computational costs, or are there other costs involved?
Computational costs, yes. Okay. So you just have to do more work to get the solution right. Yeah.
A related question, how do you assess the accuracy in your simulation?
Benchmarking. So in the end, we're extremely happy if we have experimental benchmarks that are kind of clean room that we can compare against to see what exactly happens. We can, of course, do benchmark calculations using high-level methods, and that's what a lot of people do. So there's a whole community that does this, calculate high-level benchmarks for small systems, compare to this functional, that functional, and see how accurate it is. But if you go to a larger system, you'd like to be able to know whether the larger system actually does what it's supposed to do. So in the molecular area, for us, it's really been extremely useful to have a spectroscopy around, because they will tell you what the structure is of a molecule by vibrational spectroscopy at 100 atoms or so, if the structure is reasonably solvable, and this is exactly what happens. And then we have something to compare against. So that's how to assess accuracy and how to make it better. This is in fact what we're doing.
Further questions? You must have played it very clearly. Thank you again.